Assalamu alaikum everyone. This is lecture 10 on control system engineering 1. We are discussing chapter 4, time response or transient behavior. In the last article that we covered was article 4.5. Actually, we tried to find a generalized transfer function. Okay, so basically G of S was uh, omega n squared divided by S square plus twice zeta omega n s plus omega n square. So in terms of the two system parameter, that is omega n, natural frequency of oscillation, as well as zeta, the damping ratio. Okay, so this is what we have derived in the last topic. So in this topic, we actually want to find out the formulas that we have to use to figure out the performance parameter of the second order system. And for that, actually, it is wiser to uh, concentrate on under damped scenario because all the parameter required is actually available in this scenario out of the four possible forms of the response of the second order system. So that is why we are more interested about this form under damped system response. We actually want to find out the step response of underdamped system. And based on that, we will try to find out the formula that can be applied to the similar systems, basically all four form of it. Okay, so our objective here, the first objective is to defining the transient specification associated with the underdamped response. So this is objective one, first objective, defining defining transient specifications. Specifications for the undertone scenario. Okay, so this is first objective. The second objective is to relate these specifications. So relating these specifications with pole location. Okay, so we have to see the specifications that we're defining, whether they are actually can relate those with the pole location or not. And finally, then tie the pole location to the system parameter. Okay, so how the desired response generates required actually the system component. So based on that, you have to find out the you have to tie the pole location to system parameters. So let's see how it goes. So start with the system under the system. First of all, so we have to go for the step response. So this is our system. Okay, so what we have here is omega n squared divided by s squared plus twice zeta omega n s plus omega n squared system itself, which is g of s. Then we want to have a step response r is equal to 1 by s, and that will give us corresponding output response c of s. And our formula, as always, is better to write with that one. So c of s equal to your r of s times g of s. If you put everything, then what you will get is omega n squared s times s squared plus twice zeta omega n s plus omega n squared. Okay. Now we know that we have to do the partial factor expansion. So k1 by s plus k2 s plus k3 by s squared plus twice zeta omega n s plus omega n squared. Now, on the both side, if you multiply with the lowest denominator factor, that is s into s square plus twice zeta omega n s plus omega n squared. So if you multiply with that, so what you're going to get is omega n square equal to k1 times s square plus twice zeta omega ns plus omega n square plus k2s plus k3 into s. Okay, so we can take, you can just rearrange a bit, and then what we are going to get is omega n square will be k1 plus k2 s square plus twice zeta omega n k1 plus k3 s plus k1 omega n square. Okay, so now the next thing that we should be doing is we have to equate the coefficient in the both sides. So if we equate the coefficient in the both sides, we can easily see that this one and this one has to be equal. So k1 has to be have a coefficient of 1. And then finally, k1 plus k2 should be equal to 0. So k2 has to be minus k1 equal to minus 1, as well as twice zeta omega n k1 plus 3 ak3 should be equal to 0. And from that, we can see that the k3 value has to be minus twice zeta omega n, because of the fact that k1 is 1, so we can directly write that value. So now we know all the coefficients k1, k2, k3, so we can write the output for the partial fraction expansion as cs equal to 1 by s, k1 is 1. Minus can be taken common because both of them are actually minus, so minus s plus twice zeta omega n divided by s square plus twice zeta omega n s plus omega n square. Okay, so now we have to actually rearrange the second term so that we can write a form something like this. One form can be s plus a by s plus a square plus omega square, which will be actually in the time domain will be cos omega t to the power minus 80. Okay. And the other form we have to have is omega divided by s plus a whole square plus omega square. So in the time domain, what will be actually to the power minus 80 sine omega t. So this side note. So this is the Laplace transformation. So we have to organize the second term, so it's something like this. Okay, so now let us try to rearrange. First of all, in the denominator, we have to have the square terms. Then we can actually decide what is our a and what is our omega, and based on that, we have to rearrange the numerator. So 1 by s minus the denominator, and keep the numerator as it is for now. Okay, so s square plus twice zeta omega n s. Then we can actually have zeta square omega square to make it square. Then we have to subtract that as well. So zeta square omega square plus omega square. Okay, so now 1 by s minus the denominator, what we have is s plus zeta omega n whole square. Minus, you can take omega square common. So if you take omega square common, then we have omega square. Then you have 1 minus zeta square. Okay, so numerator as it is, twice zeta omega. So let's do a little bit of more formatting in the denominator. Okay, so what we are going to get is 1 plus zeta omega n square plus omega n root over 1 minus zeta square whole square. Now this is now what is our a? Our a is now what we have figured out is zeta omega n, and what is our omega? Omega is omega n root over 1 minus zeta square. So now the numerator you have to organize in a way so that you can have this parameter at the top. So let us organize that thing 1 by s minus so s plus zeta omega n we should have. So s plus zeta omega n. So another zeta omega n will be left. Okay. So but now we can just separate these two. So okay, so now if we separate, then what we are going to get is 1 by s minus s plus zeta omega n uh, s plus zeta omega n whole square plus omega n root over 1 minus zeta square. Now, next parameter that we have, actually, we have to have this quantity here. So we bring it, we rearrange what is additionally added, and we have to subtract that. I think divided that thing as well. So 1 minus zeta omega is going to have to bring. So zeta is already there, and we bring this additional factor. So divided with that additional factor, we will go 1 minus zeta. And it will be as it is. That's okay. So now we can actually apply the formula. So this is your CS. Now taking inverse Laplace transformation, what you're going to get is CT equal to, this is 1 minus the delay is the decay is e to the power minus zeta omega n t, and then you have cos omega t. So cos omega n root over 1 minus zeta square t. Okay, then you have minus the coefficient remaining as it is, that is zeta by root over 1 minus zeta square. Then you have the rest of the thing, you can actually apply the sine formula. So you have the delay to the power minus zeta omega n t. Then you have sine omega t, that is omega n root over 1 minus zeta square. Okay, so you can we can actually take common of e to the power minus zeta or zeta omega n t. Then we have a form like this: cos omega n root over 1 minus zeta square t minus zeta root over 1 minus zeta square. And then we have sine omega n root over. Don't forget that it should be positive because you've taken the negative common. So 1 minus zeta square t. Okay, so now this is one solution, but if you want to make it look a bit better than this, then with a single trigonometric terms, so you can also do that. So, but this is one of the form. And then if you are not happy with it, then you can actually take this denominator outside. So what we are going to get is, okay, so CT equal to 1 minus e to the power minus zeta omega and t into 1 by root over 1 minus zeta square. Then you have this thing has to be multiplied, taking common, so it has to be multiplied here, root over 1 minus zeta square, and cos omega n root over 1 minus zeta square t plus zeta sine omega n root over 1 minus zeta square t. Okay, so this parameter can be considered as A, this parameter can be considered a P. So if we divide by A is root over A square minus B square. So root over A square minus, just the way we have done in the chapter 2. So A square minus A square plus root over A square plus B square will be actually basically 1. So we can directly apply the formula without further ado. We can consider this thing as actually cos phi and this thing as a sin phi. Okay, so what we can write here is finally is 1 minus e to the power minus zeta omega n t 1 by root over 1 minus zeta square. Then you have cos phi cos omega n root over 1 minus zeta square t plus sin phi sin omega n root over 1 minus zeta square. Okay, so while looking one can be something like this 1 minus e to the minus zeta omega n t, we divide with 1 minus zeta square, then cos omega n root over 1 minus zeta square t minus 5. Okay, so this is what it should look like. So this is another format. So if you are not happy with two sinusoidal signal, you can express it in terms of a single sinusoidal signal. So this is what we are going to do. Okay, so this is the two responses that we are getting. Now, based on this response, these responses are actually based on the two system parameters that we already defined, omega and zeta. Now, if we want to figure out rest of the system parameters, then what specifications, to be honest? So what specifications we have? So first specify 4 of them actually we have. So the first one is rise time as before, rise time TR. So it can be defined in terms of the time it takes to go from 10% to 100%. This is one way. Sorry, 10% to 90% is one way. Also, you can take 5% to 95%. But if you take this percentage, it's difficult to derive the formula. Only the formula is only possible with the assumption that 0% to 100% if you take. How much time it takes to go to that one? Then you'll be able to derive the formula for the rise time. Okay, so we'll be taking the help of this one from some other book. In our book, there is no specific derivation given. So this is one thing. Then we have a second specification that we have is actually a peak time. So peak time, the time it takes to reach the maximum value, that time is called so Cmax. So this is the output. So Cmax, the time it takes to reach the Cmax, that is called your peak time. Then finally, the third one is percentage overshoot. So percentage overshoot is basically how much it is going beyond our final value. Okay, so maximum value that is achieved. So this is what is called percentage overshoot, or percent overshoot times percent overshoot. Okay, so percent overshoot, this is how we express it. So the amount that the waveform overshoots the steady state value or final value. Okay, so that means at TP, whatever the level it is gaining, Cmax, so how much is the level and how much we are actually expressing in terms of the final value or steady state value. So as a comparison. Don't worry, we'll be writing the formula to clearly get the idea how we are going to write it. Then fourth specifications of the second order system is basically settling time. Settling time. settling time, and we express it by TS. And the definition is whenever the waveform reaches within plus minus 2% of final value and doesn't leave. Okay, so it doesn't leave. Okay, so all these definitions is difficult to understand without the figure. So let's draw the figure, then see how can we define all these parameters. Okay, so an under damped response, this is your final value. Okay, so C final value or C steady state, whatever you prefer. So we have response something like this. Okay, so this is your peak value. So this is your TP, the time it takes to reach the peak value. What is rise time? Rise time is, according to this book, 10%. So this is the 10%. Then say this is your 90%. Okay, so 10% to 90%, how much time it takes. So this is your rise time, TR. Okay. Now, what is settling time? So within 2%, within 2%, when it goes, enters within plus minus 2% and doesn't leave. Okay, so you have to draw both plus and minus 2% line. Okay, so whenever your curve is within that 2% line and doesn't leave. So basically somewhere here. So after this line, it doesn't leave. So this is your settling. Okay, so within plus minus 2% and doesn't leave. So this is what is called settling time. And what is percentage overshoot? The amount of the rise that you gave, C max. Okay, so how much it is compared to your steady state value. So let's say you're supposed to have steady state value of 1.5 ampere, okay? But initially it is rising up to say 4.5 ampere. So the percentage wise it will be 300 times more. So this is how you have to express the percentage overshoot. Okay, so let us try to derive the formula for all these four parameters. Before that, one thing that it should be added as a side note that what is actually phi. So your phi is basically tan inverse b less than b by a. So basically this parameter here by this parameter, so b by a, which is basically zeta y equal to 1 minus zeta square. So in case you want to know how much phase shift is there, so it is. So now we define all the parameters. Let us now try to evaluate all of them. So first of all, start with evaluating the peak time. So evaluation of TP. So what is how to find the TP? So far the solution that we have gathered is something like this. So this is the equation that we get as the response equation. So now the point is to find out the TP, we need to find out the condition for maximum value, isn't it? So the condition for the maximum value of the response. So for that, we know that how to find out the maximum minima is dCt by dt you have to figure out. And once you figure out dCt by dt, then you have to set it to 0. And that will give you corresponding condition for which actually this equation will give you the maximum value. Okay, so it's complicated to actually differentiate this equation. So instead of that, what you can do is not doing the differentiation in time domain. Another way of representing this dct by dt is dc dot. Actually, we left the chapter 3. The chapter 3, this notation is frequently used. So this is equivalent to actually dct by dt. And if you have d double dot t, that actually is d square ct by dt square. Okay, so this is the notation wise. So we have to use one of them. So instead of doing the differentiation in the time domain, setting to 0, rather actually we'll be trying to do the differentiation in the frequency domain. Let's see whether frequency domain differentiation is easier than this one. Okay, so what we have to do is basically we have to differentiate uh, DC. We have to take the Laplace transform version of it. So this is nothing but in Laplace domain. We can with an alternative representation, we can also write something like this. And this actually means that differentiation in the S frequency domain is S times of S. We already know what is C of S, isn't it? So if we multiply with S, then we have something like this: omega n square S square plus twice zeta omega ns plus omega n square. So as you can see, this S is getting cancelled out. So what is left, the differentiation term here is this omega n square S square plus twice zeta omega ns plus omega n square. So this is already the derivative. So now actually we have to find out what is it is in the time domain. So we are into the Laplace domain now, is ct dot. So we have to just organize we already know what is the denominator, isn't it? In the last case, we already derived it. So S plus zeta omega n whole square plus omega n root over 1 minus zeta square whole square. Okay, so now in the numerator, just we have to organize because there is no S term. So we just have to bring the omega here. So if we just bring the omega, then we have to bring this parameter basically. So omega n root over 1 minus zeta square. But we don't have root over 1 minus zeta square. We also have additional omega n. So we have omega n. So whatever we have bring, you divide with that. So 1 minus zeta square. So we don't have to worry much about this factor. This is just a constant. Okay. So now what we have is this is your A and this is your omega. So if you now take inverse Laplace transformation, then what we are going to get is the derivative of this one will be actually, so the derivative will be something like this. You have the constant as it is, so z omega n divided by 1 minus zeta square. Then you will have dA because of the A parameter e to the power minus zeta omega n t. Then you have sine omega n root over 1 minus zeta square t. Okay, so what is the condition for making to achieving the maximum value is the derivative has to be set to 0. So these parameters are constant. So only the fact is whenever this parameter is 0, then your c dot t will be becoming 0. So sine omega n root over 1 minus zeta square. Whenever it is 0, we know the condition for sine to be 0 is n pi. So basically what we can write here is omega n root over, don't forget the t, 1 minus zeta square t equal to n pi. So t will be actually n pi by omega n root over 1 minus zeta square. Now, what is mean by n pi? What should be the value of n? So the value of n can be 0, 1, 2, 3. So which value should take? So first of all, if you take n equal to 0, q will be also 0. So it is not what we are asking for. Rather, we are actually trying to obtain the first pick. This one. So for the first pick, n should be n should be equal to 1. For the second pick, n should be equal to 2. The third pick, n should be equal to 3. So what we are looking for is the first pick or the maximum value. So for that, we have to pick n equal to 1. So that will give us the corresponding value of Tp, and that is pi by omega n root over 1 minus zeta square. So this is our formula for finding the peak value. Okay, so next thing that we have to figure out is evaluation of your percentage overshoot. So step by step, we'll try to cover all four of them. So let's go into evaluation of percent overshoot. Okay, so percent definition wise, percent overshoot or percentage overshoot means actually C max, how much it is overshooting in terms of compared to your final value. So C max minus C final with reference to C final. Okay, into 100. Now we have to find out what is C max. We know that at T equal to TP, whatever the value of the response is given, is actually C max. So basically what we know is C TP should be equal to C max. Isn't it? Maximum, whenever it is achieved, at that time, whatever the value, that will give you the maximum value. So in that complicated big equation, so we have to figure out what is Cmax. Okay, so we just replace the T by Tp, and that will give us 1 minus e to the power minus zeta omega n Tp. Then you have cos omega n root over 1 minus zeta square Tp minus plus zeta by root over 1 minus zeta square sine omega n root over 1 minus zeta square. So now just put the value of Tp, that is 1 minus e to the power minus zeta omega n. Tp is basically pi by omega n root over 1 minus zeta square. Here as well, so if you put cos Tp is nothing but pi by omega n root over 1 minus zeta square. So this parameter and this parameter same. So they can be cancelling each other. So you can write that cos pi plus zeta by root over 1 minus zeta square sine pi. So sine pi is always 0. So you don't have to bother about the second term. So what we are going to get is first term is actually minus 1. So what we are going to get is 1 plus e to the power minus omega n getting cancelled out. So e to the power minus zeta pi by root over 1 minus zeta square. So this is our maximum value. So according to the definition of percentage overshoot, so percent overshoot will be C max minus C final. Okay, so what is C final? C final is definitely 1 because step response. So 1 plus e to the power minus zeta pi divided by root over 1 minus zeta square minus 1 divided by 1 into 100. So basically 1 getting cancelled out e to the power minus zeta pi by root over 1 minus zeta square into 100 is your percent overshoot. Okay. So this formula is to figure out what is your percentage overshoot. But in general, more practical thing that we face in general is we actually have to do the reverse one. Where basically what we have to do is percentage overshoot, how much we should allow. That will actually dictate what should be the value of your zeta. So basically, percentage overshoot will be provided in most of the cases. And then actually you have to find out the corresponding zeta value required for. Okay, so in that case, what you have to do is let us try to find out what is zeta from your percent overshoot. Okay, so now percent overshoot, you just divide that percent overshoot by 100. Okay, so equal to you have e minus zeta pi by root over 1 minus zeta squared. So take it in the other side. So ln percent overshoot by 100 equal to minus zeta pi divided by root over 1 minus zeta squared. So you just multiply both sides, square the thing, then what you will have is ln square percent overshoot by 100 equal to zeta square pi square, then you have 1 minus zeta square. So if you cross multiply, then what you are going to get is ln square percent overshoot by 100 minus zeta square ln square percent overshoot by 100 equal to your zeta square plus pi square. Now, if you take this parameter in the other side and take common, then what you're going to get is zeta square equal to pi square plus ln square percent overshoot by 100 equal to your ln square percent overshoot by. So what you're going to get here is zeta square is basically ln square percent overshoot by 100 divided by pi square plus ln square percent overshoot by 100. So zeta value will be plus minus should be there, okay, but we are giving minus ln percent overshoot by 100 divided by pi square plus ln square percent overshoot by 100. Okay, so this is the formula most frequently if we have to do the you have to calculate the we will be providing a specific value of overshoot. Based on that, what should be the value of the zeta? So to calculate that, this is the formula that we have to use. Okay, so the second evaluation is done. Percent overshoot is calculated. Now the third thing that we have to do is we have to calculate the value of your the settling time. So evaluation of settling time. Okay, so what is settling time? It says the response should enter within plus minus 2% of your final value, and it should not leave that boundary of plus minus 2. So we know that the solution has a form like this: 1 minus e to the power minus zeta omega mt by root over 1 minus zeta square. One of the form is something like this. Then we have cos omega n root over 1 minus zeta square t minus 5. Right? Now, definitely, this is a variable term. It's going moving up and down. So, for simplicity of the derivation, we are considering this one. The average value is always around that steady state value. So now, next thing is this value is the decaying amplitude. So whenever this amplitude is within plus minus 2%, okay. So then actually we have to we can find out whenever it is happening, that corresponding time is actually settling time. So the magnitude we can write in that way. The magnitude into the power minus zeta e to the power minus zeta omega n ts. We write it in that way. 1 minus zeta square should be equal to 0.02. Okay, so whenever the magnitude is reducing to that value, okay, so then we are within the range of plus minus 2% of final value. Okay, so basically 98% or 102, 102%. So 102%. So now just cross multiply. So what we are going to get is e to the minus zeta omega n ts equal to ln equal to 0.02 over 1 minus zeta square. So minus zeta omega n ts will be ln 0.02 over 1 minus zeta square. So ts can be calculated as minus ln 0.02 over 1 minus zeta square zeta omega. Okay, so TS formula is a bit complicated, and based on the value of zeta, the value is always going to change. But for simplicity of the analysis, this numerator value, actually, if you range the value of the zeta from 0 to 0.9, then this value of the numerator is going to range from 3.91 to 4.74. So this is the range of the numerator. So for that, actually, we can assume a suitable value in between. So the most commonly used suitable value is 4. So 4 by zeta omega. So without memorizing that complicated formula, this is the assumed one, simplified version. Okay? So this is your formula for the settling time. 4 by zeta omega. Okay, so this is how to calculate the value of your settling time without making things too complicated. Now the last one is evaluation of your lifestyle. Evaluation of PR. So as we said, if you start if you try to derive from 5% to 95% value, or if you try to go from 10% to 90%, then it actually is difficult to derive. So that is why in another book, in our book, in the book that we are following, mainly, they haven't given the derivation, but in some other book, they have used from 0% to 100% how much time it takes to go. So based on that, they have derived it. So this is also an approximate model of deriving it. So final value is final value that we are trying to figure out here. So CTR, it should be 90% or 95%, but we're taking it 100% or maximum value, how much time it takes to reach. So CTR is going to be 1, and our formula is 1 minus e to the power minus zeta omega n TR cos omega n to the power 1 minus zeta square TR plus zeta by root over 1 minus zeta square sine omega n root over 1 minus zeta square. Okay, so as you can see, one I'm getting cancelled. What is left is basically the minus value that we had. So e to the power minus zeta omega n tr into the this parameter, that is sinusoidal variations omega n over 1 minus zeta square tr plus zeta by over 1 minus zeta square sine omega n over 1 minus zeta square tr. So this parameter is going to be cannot be zero, so we can actually make it vanish to multiply with the other side. So what is left is this parameter. So now you can just rearrange a bit. So say cos omega n root over 1 minus theta squared pr equal to minus zeta root over 1 minus zeta square sine omega n root over 1 minus zeta squared. So we can divide sine by cos, and we can take this into other side. What is will be left with is tan omega n root over 1 minus zeta square. Here should be equal to minus root over 1 minus zeta square by zeta square. Zeta. Okay, so now this is what we have. So what we can write is omega n root over 1 minus zeta square tr should be equal to tan inverse minus root over 1 minus zeta square by zeta. Okay, so here we can multiply both side by omega n, numerator and the denominator. So what we will get here is tr equal to 1 by omega n root over 1 minus zeta square. Then you have tan inverse two parameters. So omega n root over 1 minus zeta square and zeta omega. So there should be a negative sign as well, negative sign. So whether you have noticed or not, these two quantities that you have obtained here, they are actually the real and the imaginary part. Okay, so this is minus zeta omega n. Then if your pole is here, pole is here around here, so that is your omega n, j omega n root over 1 minus zeta square. So it is advisable to give them indicators here rather than the numerator. Okay, so this should be okay. So now another thing we can actually assume. So if we draw a line to the center, so if we can take the theta here. So then what we can say that tan inverse or tan pi minus theta, tan pi minus theta will be actually your the height divided by the base. So basically omega n root over 1 minus zeta square by minus zeta. So tan inverse this parameter can be considered as, so tan inverse omega n root over 1 minus zeta square by minus zeta omega n can be written as pi minus theta. So what you can write here is basically pi minus theta divided by omega n root over 1 minus zeta square. Okay, so one thing we haven't said that for the damped frequency oscillation is basically this one. Okay, so this is the damped frequency oscillation omega d, and this is your sigma d. Okay, so real part we call sigma d. Okay, so exponential decay, and the frequency that we have obtained is basically omega d, or damped frequency oscillation. So if you want to represent the thing in terms of damped frequency of oscillation, you can also do that. So pi minus theta by omega is actually theta. Okay, so this is how it has been done in this and other book that we are taking the reference from. I think we got a book. But in our book, the Nice's book, they actually haven't derived the formula because of rather than they actually use one figure that helps us to, if you know the damping ratio value, this is a normalized rising rise time curve, something like this is being drawn. And in this axis, what we have is TR times omega n, normalized rise time in this axis. And in this axis, you have zeta values. So if you know the zeta values, you can find, also you know the omega n, you can find out the corresponding location. Then you can find out the corresponding values, divide the value with TR, then you can find out what should be the value of your rise time. So you can go for both of them, either go for the table or the chart diagram, or you can derive it by yourself with the formula that we have derived. But you have to always remember that we have assumed the condition that we're actually reaching from 0 to 100%. But in most of the cases, it is 10% to 90% or 95% to 95%. Okay, so now let us take one example, example 4.5. Example 4.5. So in the example 4.5, a transfer function given g of s equal to 100 divided by s squared plus 15s plus 100. So what you have to do is you have to find out what is TP. You have to find out the percentage overshoot. Then you have to find out settling time. Then you have to find out the price time. So now, we already know the formula for the peak time. Peak time is basically pi by omega n root over 1 minus zeta squared. But whether you have noticed or not, root over pi by n is omega n into root over 1 minus zeta squared is also the imaginary part of the root. So basically the omega t, j omega d equal to j omega n root over 1 minus zeta squared, damped frequency of oscillation. So this can also be written in terms of something like this, pi by omega d. Okay. Now, what is your omega n? Omega n square is actually 100. So omega n is actually 10. And what is our zeta? Okay, so zeta is twice zeta omega n equal to 50. So zeta will be 15 divided by 2 into 10. So 0.75. Yeah, so you can just put the values here. So pi by omega n, that is 10 root over 1 minus 0.75 whole square. So this will give you approximately a value of 0.475 seconds. Okay, so this is how you have to calculate the value of the peak time. The next thing is finding the percent overshoot. So the formula for the percent overshoot is e to the power minus zeta pi by root over 1 minus zeta square into 100. So we already know the value of zeta. So e to the power minus zeta, that is 0.75 equal to 3.14 approximately divided by root over 1 minus 0.75 whole square into 100. So that will give you a value closer to 2.838%. Okay. So next, the thing that we have to figure out is what is the value of the settling time. So formula for the settling time, you can go for the original formula, that is minus ln 0.02 into the over 1 minus zeta square. Okay, so this will give you precise value for zeta omega n, which is zeta omega n is nothing but uh, or you can go for the approximate formula of 4, and zeta omega n is the value of sigma d. So which one you prefer, you can go for that. And if there's the value of 4 with 0.75 into 10, so that will give you a value of 0.5337. So this is your settling time. Now, rise time, since this book hasn't provided any formula for the rise time, so they are actually using the curve that is provided. So according to the curve, according to our estimation, our zeta value is 0.75. So somehow we have to find out the 0.75 somewhere here. Okay. So from the 0.75, then we need to find out the corresponding value in the other axis. Okay. So the book says this value is 2.3. So basically what we have is TR into omega n equal to 2.3, and our omega n is 10, so TR will be actually 2.3 divided by 10, that is 0.23 seconds. Okay, so this is a very simple way to calculate the rise time using the figure that has been given in this book, or also you can also use the formula that you have derived here, which is pretty close to the formula that you are using for peak time as well. Basically, that is repeatedly coming back, so that is why they have a similar pattern. Okay, so next thing, actually we haven't yet finished this topic, but these are actually very important, the topic that we are going to discuss next. So the pole location that we have figured out so far. Okay, so pole location that we have figured out, say this is what we tried to find, and this is your j omega n root over 1 minus zeta square, which is j omega d, and this is your minus zeta omega n equal to minus sigma d. Okay, so always you remember there's a complex conjugate, because the complex or imaginary pose doesn't appear alone. It always have its complex conjugate. So now let us try to find out. We already said that we assume this angle to be theta. So we have to find out what is this length then. So using the Pythagoras, we can easily figure out what is this length. So it says this is 0, this is point A. So the length 0 to A can be given as square root of the real portion, that is zeta omega n whole square plus omega n 1 minus zeta square whole square. So basically what we are going to get here is zeta square omega n square plus omega n square minus omega n square zeta square. So this parameter can cancel out. What is left is omega n. So you can easily say that this parameter here, this length is nothing but omega. Okay, so next thing that we have to actually relate is that how these uh, specifications that we have defined as related to the pole location. Okay, so uh, the peak time that we have related, time was basically pi by omega n root over 1 minus zeta square. We can easily relate this thing to pole location, isn't it? So pi by, this is nothing but omega d. So imaginary portion of your pole location, imaginary portion of the pole location is actually controlling the peak value. Okay. So if the imaginary portion is higher, peak time is lower. If the imaginary portion is lower, then the peak time is higher, inversely proportional. So we can easily relate the pole locations, imaginary portion, with peak time. Okay. Next thing is the settling time. So the settling time. So your settling time is basically uh, 4 by approximate version of it is 4 by zeta omega. What is zeta omega? Zeta omega is nothing but sigma d. So actually, real portion of your ball location is related to the settling time. So how much time it will take to get even 0.1 plus minus 2%. So that is actually defined by your sigma value. So if the sigma value is higher, the time taken will be smaller. If the sigma value is lower, the time taken for the signal to get settled will be, uh, if the sigma value is lower, then it will be higher. So inversely proportional. Okay, so this is how they are related. So basically, as you can see, the location of your pole is actually uh, determining the behavior of your system. So system's response behavior or specification, the TP, TS, or the TR. So all are actually related to the location of the port. So let me stop it here today. We have to discuss in detail the relation with the pole and the behavior in detail. So we'll continue the same topic. It's not yet over. So article 4.6, we'll continue with this one in the next class, in the next week, inshallah, as well. Assalamu alaikum, everyone.